Now we're good, right? It's not frozen, it's not being crazy. Ay, ay, ay. So if we put slices of bread together, we get a loaf. When we put slices of watermelon together, we get the whole watermelon. Slices of tomato together, we get the whole tomato, etc. However, question, all of these up here, is this two-dimensional or three-dimensional? Why? I agree. Why is it three-dimensional? Because it's bread. That's true. But the slice of bread, it's three-dimensional, really? It's volume, which means not only does it have length and width, but it also has depth. Well, yeah, but it has, you can say it different ways, right? Base and height and then depth, or length and width and then depth. You can touch the bread. You can eat the bread. The bread can fill you up. True? If you're on a diet, you want to avoid the bread. But anyway, well, depending on which one you're on. But this is three-dimensional because it has depth. So how could you make this closer to two-dimensional? Slice it. Not in half. It'd still be just as three-dimensional, just lower volume. How could you get closer to the second dimension? Slice it thinner and thinner and thinner. Now, it's bread. I mean, eventually, you can't slice it any thinner. But in your minds, can you think of slicing it thinner and thinner and thinner? Because two-dimension has no what? Think a rectangle versus a rectangular solid, or a square versus a cube, or a circle versus a sphere. No depth. So, could you feel a slice of bread that was two-dimensional? No. You could see it, you could, yeah. But when you went to go grab it, what couldn't you do? Through your fingers. Why? Because there would be no depth. There would be nothing to hold on to. Could you eat it? Well, I guess you could eat the area of it. That's weird. That's awkward. But why am I saying that? You could actually touch, you could feel, you could eat this slice of bread. But if we were thinking a two-dimensional slice of bread, it would slip through your fingers. Here's the weird thing about volumes by slicing. The same way that we accumulate three-dimensional slices, or we could think of putting three-dimensional together to make like an actual solid, like a loaf of bread, we can actually accumulate two-dimensional slices also, which is weird though. Hold on. So you're telling me if I were to pick up a two-dimensional slice of bread, it would slip through my fingers. Then how on earth is it different if I accumulate infinitely many two-dimensional slices? In some ways you would think it creates depth, but in other ways maybe you would be like these monks way back when that basically called this branch of math heresy, because they were like, you can't make something out of nothing. What do you mean nothing? There's no depth. So if you put together infinitely many, what should there still be? No depth. And yet there is. It's all made possible by an integral. Okay, so what's going on? These pictures, and maybe some of you are like, oh, this is fun. I want to do three-dimensional pictures. This is kind of cool. Number one, they're more regular, geometrically speaking, than these ones over here. I mean, the tomato was okay. The tomato and the orange, maybe even the lime, like they were somewhat like a circle, like a sphere. But come on, let's be honest. That's not a rectangle, right? That's not a triangle, and that's not a, I don't know what that is. But anyway, those are more geometric. We're going to be seeing geometric shapes, but we're also going to see shapes that are not geometric, but have geometric slices, meaning like known shapes that you guys have. So the goal is to find the volume of three-dimensional figures. We're going to be using cross-sectional slices. So cross-section's a new vocab term for these slices of three-dimensional figures. And we can't, by hand, accumulate two-dimensional, but we can accumulate three-dimensional and then try to get rid of the error. Now, we're going to go over to those ones and talk about those ones, but first of all, I did have a link to another calculus class that I think takes a little bit more time, meaning they cover calculus in honors pre-cal, like a semester of it, so they have more time during the year to spread things out. But they've done some kind of cool calculus projects. Let me turn off the front light. This is called approximating with cross-sectional slices. Now, guys, is a vase one of those like surface area, volume shapes that you learn in geometry? No. But if you look closely at this vase, question, what shape are the slices? Can you see? It's coming out. It's three-dimensional. Can you see them? They're circular. Technically semicircular, because I'm pretty sure they cut it off. I'm pretty sure they don't have it going all the way around, but they're semicircular. What else do we have? If you are talking about a drop of rain, is this one of those shapes you would have learned, the surface area or the volume to? No, but can you guys see that they literally have this suspended in this little like first quadrant sort of deal, and they used fully circular cross sections or slices, right? If we were to look up at some of these other ones, where's the shark one? The shark one's cool. That one's like a sine curve. They're going all crazy. That's a golden egg. I don't know what that is. Let's see. Where's the shark? Baby shark, doo 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 doo. Baby shark, doo 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 doo. Oh, the snowman. That's there he is. Can you see the shark? Can you guys tell what the cross sections are? It's kind of hard to see. Not circles. You would think it was, but this one's actually triangular. I think they're isosceles triangles, if you can tell. And like he added some little embellishments. Yeah. But he was using isosceles right triangles along the way, if I remember right. I think when I clicked in, I could see it a little bit better. But anyway, you can make volume approximating with geometric shapes that we do know. But I want you guys to look at this raindrop. Is there anything off with this raindrop? Is there anything that's not quite perfect because of the slices? I know it's fuzzy. Ignore the fuzziness. Oh, where's our raindrop? He's down lower, huh? There he is. Is there anything that's imperfect? Can you guys tell, despite the pixels? Yeah. What would the raindrop actually be? Smooth. So why are there ridges? Could you, if you could measure the radius of each of these little slices, which is what the project actually does, they have like spreadsheets and they've actually added it all up, could you find the volume of each of these little slices? Yeah, pi r squared h, no big deal. And it would be exact, pi r squared h, right? Because as long as they cut them circularly, which I'm assuming they did it and they did it well, as they were going through, if they could define this by a function, and if they could find all the different radii using the set heights, they could actually add up the volume, but would it be exact? Because of the little baby ridges, right? It could be an over approximate or it could be an under approximate. Oh, what's this sounding like? It's approximating, but not exactly. We're using like little depths and we're using like little heights, or in this one it'd be radii. We're adding them all together, but it's going to be off. What is this like? Right and left and midpoint Riemann sums, trapezoidal sums, remember? Do you remember how that was kind of segmented too with those rectangles when this curve was smooth? But how did we get rid of the error then? We took a limit. Do you remember what we took a limit of? The definition of an integral. Might have been a while. I could actually show it up in here just in case someone's absent today. The definition of an integral. Let's go back before notes. Ooh, that's not the place I wanted to put it. Hi. How are you this morning? Doing well. Okay, there we go. It's scary when a teacher starts talking to her smartboard. Okay, the definition of an integral. Doesn't have something to do with this. What does that mean? Who do you have? Some sort of f of x. What are you doing with that f of x? On some sort of interval, which is kind of ironic because it's not actually shown like in the definition. On some sort of interval, what does a base times a height signify? Area. So aren't we technically doing... Oh, wait, hold on. The way I defined it, we're actually not coming from the left. We're actually coming from the right. Lo siento. So it'd be like this. And if n was a finite number, what's going to be the problem? If I only fit in 10 rectangles, and I think I just approximated, it might not have been 10, But if I add all these together, just like the raindrop, what's going to be true? It's not going to be exact. There's going to be some error. But I'm not saying fit in 10. I'm not even saying fit in 100. I'm not even saying fit in 1,000. What am I saying? Guess what's happening to these two-dimensional rectangles as n goes to infinity? And in this finite space, you fit in more, so it's smaller bases, smaller bases, smaller bases, smaller bases. What's happening to these two-dimensional rectangles? They're approaching the first dimension. If I actually fit in an infinite number of rectangles, I am accumulating one-dimensional sticks that have no depth, and I'm somehow getting area out of it. We've been doing the impossible all along every time we did an integral. Because you could add up all these and say, ha-ha! But if I go the limit as n goes to infinity, technically we're taking areas that have approached the one dimension, and we've added up one dimension to get two-dimensional, or one-dimensional rectangles, which is an oxymoron, to get two-dimensional things. So we're going to take that exact same process and we're just going to apply it to volume. And how do we do that? Well, first of all, the very, very, very first thing is we have to ask ourselves dx or dy in a given situation. The same way that our rectangles in Riemann sums needed bases, our slices need depth. The same way our rectangles in Riemann sums needed bases, our rectangles need depth. Now, it might be kind of hard to see in this one. I was kind of trying to show it with shading. I was doing it on my iPad at some point, I think. But do you guys see the depth to this slice of bread? Sorry, like a slice of bread. Do you see it? There's depth to it, yeah? And that depth, is it horizontal depth or is it vertical depth? Horizontal depth. So I say, oh, this should be a dx. So somehow, to find this volume, I'm going to accumulate from A to B. Somehow, I'm going to put in a length times a width times a, now it gets a little bit iffy. So I can do length, I can do width, I can do height. So I guess in this one, I could kind of say my length and my height are going to need inside my integral and my check it. My length and my height and my depth. I'm putting in the third dimension, except my dx is going to be that depth. He and the integral are going to make these infinitesimally thin. So I'm actually only putting in what looks like an area formula. It looks like the area of a rectangle. But put in the dx and all of a sudden now I have my three-dimensional. So what the integral is going to do is it's going to take these like the range segmented, jagged edges, and it's going to say, oh, don't worry, I got you. Because the integral is going to make them infinitesimal to where there's no error and everything is going to be smooth and it's going to be perfect. And that's very similar to what this one would be down here. Except this one, do you guys see the depth of this slice? It's a square, but it's a square that's been given a depth. And is it a vertical depth or is it a horizontal depth? Vertical. So he's going to be a dy. And in this one, my volume, let's just say that was a squared. I could say s squared times, I'll just put height. S times height would give me length times width times height. I'm going to throw into an integral, somehow based on some sort of boundaries that we're going to figure out. But my height is going to be my dy, and so really all I need is s of y squared. So it's going to look like I'm putting in areas, because in some ways I am. This is called volume by cross-sectional areas. But the integral gives it the depth, and the depth with the integral says, don't worry, I'll make you infinitesimally thin, and I'll accumulate the two dimensions to make the three, or the two-dimensional slices to make the third dimension. It's really crazy if you think deeply about it, because it really feels like it's impossible. And yet it's possible all because of this little guy that we learned at the very beginning of the year called a limit. And the limit says, okay, take what makes sense. Adding all these to get an area makes sense. And then see the pattern, see what the sum converges to, see what the limit as n goes to infinity would be. And guess what? The impossible becomes possible. We can actually, in an essence, accumulate the one-dimensional to get two dimensions. Or here, We can accumulate, imagine infinitesimally thin, accumulating the two-dimensional to make the third, which is actually really crazy. I wish I had more illustrations. You guys can kind of see it here, because what have they not done to the slices in any of these? They haven't given it depth. Now, is it possible for us to add together? No, it's not. But what is it possible for an integral to do? Give it depth dx, or give it depth dy, or give it depth dy, or give it depth, something awkward, not x or y. Don't worry, we won't be doing ones like that. But to give it depth and say, okay, with the integral, don't worry. Not only will I give it depth and make it possible, but I'll also accumulate it perfectly. Now, you guys can kind of see some things here. Don't worry, though. I have a forever card coming. And here it is. How do we find volume? Does that sound so bad? It's not horrible, right? I think it's moved down a little bit, so it's not shining quite on the board. But the main idea, three-dimensional figures can be generated, which sounds a little weird unless you think about like a generator. What's a generator do? It creates electricity or power, right? So generator, you're making something. I know it sounds a little weird, but generator, to generate, you're making something. So the third dimensional or the three-dimensional figure or the volume are made, generated by translating a region or an area through a distance h or y. But the better description, actually, you're taking three-dimensional slices, you're stating them, defining somehow with function notation, somehow with algebraic expressions. You're making the depth a dx or a dy with an integral. That instead of with the integral working with the depth, it won't be the raindrop, it won't be jagged, it won't be off, it'll be perfect. Because they'll make those slices thinner and thinner and thinner and thinner, which will get closer and closer and closer and closer to the perfect. If the integral is a limit as n goes to infinity, as long as that number is finite, as long as the limit exists, as long as the sum converges, booyah, I got my volume. Volume. So, guys, what forever card are we? 44? Am I right? Is that close? 40 what? Okay. Volumes of solids with cross-sections. And you can say cross-sectional areas. You can say cross-sectional slices if you want to put a few more terms on there. The AP guys would probably use areas, but you could also use slices if it helps. Cross-sectional areas or cross-sectional slices. If the cross-section or the slicing is perpendicular to the x, you can also think for this one, maybe do a different color. The depth is dx. Because that's what I was just showing you guys, the depth is dy. Wait, 41 or 44? 44. Okay. 41 wouldn't make sense, but for some reason I thought someone might have said that. Let's go ahead and do a dual page, but thanks guys for helping me out. You're not going to be able to see the example very well. We have these written down though, right? Forever card number 44? Let's zoom in on the example. Now, some of you are going to be like, I can't draw that. Okay, it's okay, it's okay, it's okay, it's okay. For some of you, it's going to be really helpful to draw, but for others of you, it's not necessary. Now, there technically is a nice little link to that as well. But let me show you what, based on just the wording of the given, okay? They've shown you a cool picture in homework. Some of them are going to be cool pictures. But check it. Guys, don't we technically have two functions right there that are just two-dimensional, like normal, plain old algebra 1 kind of stuff? Okay, so if I was to make this one green, who is that guy? He's a line with an intercept at 1 and a slope of 1 over 1. Okay, whew, that's a little scary. So 1. Okay, so if I was to do starting at 1, going up 1 over 1, up 1 over 1, up 1 over 1. Okay. Good? Okay. Who else do I have? Who's this guy? Parabola. That's been shifted down 1. So I have this guy, right? Now with parabolas, it starts to get messy. You're like, I don't know, just swoop, there he is. Okay, fine. Be lazy and just plug in stuff. We know that at 0, it's -1. At 1, where would it be? 1 minus 1 is 0. Good. At -1? 0. Oh, hey, look, they intersect right there. What about 2? So at 2, 3? Oh, look where else they intersect. Hey, if I was just graphing those two, couldn't we do like a little area between guy? Right? And for area between, what would be more natural? Top minus bottom or right minus left? Top minus bottom. Hold on. Let's see. How did they say that we're supposed to slice this? Yeah, when it says cross sections perpendicular to the x-axis, I want you to think if it was all drawn out and if this was down on a table and if you had a knife in your hand and this was some sort of solid, you're slicing it perpendicular to the x-axis. Does that make sense? So you're slicing it this direction, not this direction, but this direction. That's what that means as far as perpendicular to the x-axis. So I'm slicing down. Can you guys see this in these pictures? Where is it? Oh, wait. Hold on. I have my x and y like this. Where's my x and y in these pictures? Do you see it? So if I was to show my pictures, do you guys see the line back here? Do you see the line? It's been put down on the table. And do you see your parabola? Oh, hey, that must be the intersection point. Oh, that makes sense. That's going to be the point 2, 3. Do you see the parabola at 0, -1? And then do you see the parabola going back? And there's our other intersection point of -1, 0. And then do you see the slicing happening perpendicular to the x-axis? Not this way, but this way. So what's that depth, cool kids, of those slices? Is it a dx or is it a dy? Do you see that horizontal depth of dx? So how would we find the volume if the volume formula says, no big deal, just figure out, because everything's dx in this one, perpendicular to the x-axis, and according to my picture, top minus bottom. I need to somehow think of, okay, what area are my slices? Put that in, that gives me the depth, and then it's going to accumulate them all for me and find that volume. So guys, what's the area of a square? Base times height, but remember a square, base and height's the same thing, right? So s squared or side squared. So what can I do in my integral? I can say v is equal to the integral from -1 to 2. Oh, aren't those the natural bounds? Natural bounds, section 6.1, intersections. Of who squared? S of x. I need s, but I need s in terms of x. Well, how on earth am I supposed to figure out what s? Wait, check it. Do you see the side of the square hitting the green on one side and hitting the blue on the other? What does that remind you of? Section 6.1, top minus bottom. Isn't it area between? If I was to take away the whole three-dimensional and the slices and all that jazz, isn't it just this guy? And aren't I just caring for each square, for each one that's going to be in there? I'm just caring about top minus bottom. Guys, didn't we have a way of writing top minus bottom back in section 6.1? What is top minus bottom? Top is green. Who is green? X plus 1. Cool. Bottom is blue. Blue is x squared minus 1. We are applying the ideas of section 6.1, how to get area to now get volume. Because our area between our top minus our bottom is going to be a measurement for a dimension that we can throw into a geometry formula and then solve. Why am I going to do a dot, dot, dot? Because I'm horribly mean or because that's not the point of this section? How would you finish? Solve. Plug in. Oh, don't plug in yet, right? What do you have to do first? Rewrite, simplify, then anti-derive, and then plug in f of b minus f of a. Oh, but what if we're allowed to use our calculator? I know, sometimes you can. Remember, I let you do that in section 6.1. Graphically, I let you just use the calculator. But what else do you have to be able to do? But whether you're using your calculator to solve or solving by hand, are you going to get the right answer if this is set up wrong? So what's the first point? So what do you guys think changes here? When I have the exact same green as my above, I have the exact same blue as the below, I have the exact same intersection points as far as -1, 0, and 2, 3. What changes? My shape. You guys can tell these volumes are different, right? Who's my shape? What's area of a rectangle? Base times height, but what can I do? What'd they tell me about height? All of them. Do you see how this whole shape has the exact same constant height? Why does this one change? When the side gets smaller, what's going to happen to the height? It gets smaller, because remember, they have to be the same thing. So you're going to have like a little square here, and a little square there, and a little square there, and all the ones in between. But this one, what's true the whole time? Height is 1. So what does that change as far as this? Nothing here, still the same bounds. Nothing here, still a dx. I'm still perpendicular, or slicing perpendicular to the x-axis, but what is this? Do you see it? Base times height instead of side squared. But I need base in terms of x. Okay, fine. Come up here and say, isn't this my base? That's my 1. That's my base. Whose base going to be? Isn't it still top minus bottom? Who was top minus bottom a second ago? The same thing it is now. So what is it? Yeah, x plus 1 goes first because he's the bigger. Minus. And I don't have to square anything this time. It'll be even easier to solve. Why am I going to do a dot, dot, dot? Because whether you use a calculator or by hand is review, calculator is review, but the new thing was how to set it up. Guys, how crazy does this seem? Thomas. If they didn't give us any clue about height whatsoever, and they just said rectangles, it'd be an impossible problem. Because the base would be defined by the curves that I could actually state. But if they don't tell me any hint about height, it doesn't have to be the same as base like squares. So they have to give me something. Now I have seen them say something like, whose heights are 3 times the base. So you could do like, oh, 3 times b, and I know b, and I can plug that in. Or you could do like a b times 3b is 3b squared and make your own new little formula. But they have to give you some sort of hint about height, either a number, a constant, or something, how it relates to b. Otherwise, it's impossible because that could go on forever. We don't know. Make sense? Yeah. And that's why the different shapes they're going to fit in or have you work with cross-sectional areas are going to be ones that you know and can be defined in one variable, or if it's defined in 2 variables, they give you a clue for it. So that means something like an equilateral triangle. Why would that one be okay? all the sides are the same. And so if you have the top minus bottom, like for the side or like for the base, the top minus bottom could be the side of the triangle. Uh-oh, but isn't a triangle 1/2 base times height? We'd have to do some geometry and remember, okay, but it still is dependent on one length being defined. What's something else? How could a semicircle be okay? Just the area formula is 1/2. Semicircle though, 1/2 pi r squared. So the whole formula is based on one variable. Now we'd have to kind of think about the picture as to who r is, because a semicircle, Guys, what if we were to take this exact same example, just because I have tons more, but since time is running short, what if I was to take the exact same example? Can you guys picture what would happen if there were semicircles coming out of it? We would slice it. What would be coming up? Do you see how it would have depth again? So what would change? My area formula. Who's R? It's not top minus bottom, because who's top minus bottom? How does diameter and radius relate? So I could do 1/2 pi top minus bottom all over 2. All right, get out of here. Kiddos, maybe peek at homework. Maybe peek at homework. But otherwise, keep an eye on Google Classroom for that announcement that will come today. I apologize for it not coming earlier. Bye, kid.